Okay, we've talked about what is a local maximum or minimum and what's our goal in optimization. And we talked about an approach which is Fermat's theorem. And Fermat's theorem gives us the strategy that we should start by identifying a list of candidates, which is the critical points. And once we have that list of critical point candidates, we should look at them and try to see, are they a local maximum or minimum? Okay, so there's a couple of different ways that you can look at a point and try to tell if it's a maximum or minimum. And we're going to look at two of them. The first one is a contour plot test. So the idea is illustrated in this picture here. If our graph has a, well, in this picture it's a local minimum, so the bottom of a valley, then that local minimum picture gets reflected in the contour plot that's here. Remember, a contour plot is where you cut horizontally across and look and see what the curves look like. The horizontal traces are these horizontal slices, the sort of blue lines here along the graph. I'll draw them in purple. Well, I guess they go all the way around like this, and those are the horizontal traces, and if you draw them on the XY plane, you get the contour lines. And look what happens in this valley. Since the horizontal traces circle all the way around the sides of the valley, you get closed curves that loop around. You get loops, and they all circle around the bottom of the valley. So these contour lines circle around the minimum. So let's write that down. We get contour lines are closed loops that encircle the minimum. They don't necessarily have to be circles. This valley could be distorted. It could be a long, skinny valley. So maybe I shouldn't say encircle, because they don't have to be circles. What if I say enclose? Maybe that helps avoid any wrong impressions. All right, that's what happens for a local minimum, and it's going to be similar looking for a maximum. If we turned this graph upside down to make it a hill, then the horizontal traces would still loop around the sides of the hill, and you'd still have looping around contour lines in the case of a local maximum. Okay, now let's switch over to the other one, which is a critical point that isn't a maximum or a minimum, a saddle point. Now, it looks more complicated, right? And you can see what happens on the contour plot. You can see that there's two directions where the function is decreasing, and that means that you go into contour lines with lower numbers, and there's two directions towards the mountains where the contour lines, where the function is increasing, and you get into contour lines with higher numbers, and you have this sort of X or cross thing going through your critical point, and there's two directions where the numbers are increasing and two where they're decreasing, and none of them circle around the critical point. So this is an example of a contour plot at a critical point that isn't a maximum or a minimum. Another picture, this is a plot of the function x cubed plus y cubed minus 12xy. So there's a graph here. It's a little bit hard to tell from this graph, but it dips down into a valley there, and then it comes up through this mountain pass and dips down into another valley on this side of the mountain pass. But it goes up to the mountains on the two sides of that pass. So you have a saddle point here, which the way they've drawn it, they made it so the saddle point would be right at the origin, and that valley is sort of behind it. In the contour plot, as expected with a valley, if you took a level walk without going up or down, you would circle around the sides of the valley. So from this valley, every direction is increasing. So in every direction, you're crossing the same contour lines, because you're increasing to the same altitudes. That means that those contour lines fully enclose the local minimum point. But at the mountain pass, you have the same kind of description that we saw before. There's a there's a sort of X at this point. They don't stay. Those contour lines don't stay straight lines forever. They sort of go a straight line and then come up and join the rest of the contour lines. Like it would go up like this in between the ones that they drew, and then crosses and goes up in between that way. So they're kind of bent, but at this critical point, those contour lines cross each other, and then you can see that none of the contour lines go around that point. So that's what makes it recognizably a critical point that isn't a maximum or a minimum. Okay, so that's our first test for maximum or minimum. If you have a contour plot, you can look at it and see, do the contour lines go around the point or not? The test isn't always useful. If you don't have a contour plot handy, or if it's too complicated, then maybe this isn't the test for that situation. But if you did have a contour plot, then this test is perfect for that situation there.